Well, thanks everyone for joining us for AJ's Master's Technical Report. Let me give you a short background of AJ before he starts his presentation, and then we'll go ahead and jump in with the formal presentation. So AJ, in terms of his educational background, has an Associate of Arts degree from Otero Junior College in Southeast Colorado. And then he moved over to complete a double major in soil and crop sciences and ag business here at Colorado State University. So that's his educational background. Just to mention a few of his professional experience afterwards. He was a research assistant at the Arkansas Valley Research Center of CSU down in the lower Arkansas Valley. And in fact, that's where I met him the first time when he was still a high school student over there. And then he did an internship with Centennial Ag Supply as an agronomist, a field rep, covering the South Platte Basin area. And currently he's assistant director of the Irrigation Innovation Consortium, helping with the research and also the administration aspects of the consortium. In terms of recognition, he has had quite a bit of recognition in terms of academics and research. Most recently, he was CSU Vice President for Research Office Fellow back in 2018 to 2019, recognized for his research, grad student research. And also, he was the commencement speaker for his graduation here at CSU in the College of Ag. So just among the many recognition that AJ has received through his career. And now he's gonna give us a presentation on a technical report for his master's program, focusing on the work that he did in the lower Arkansas River Valley with me and of course his co-advisor, Dr. Tim Gates in civil engineering, who is also in the room, and also collaborating with Dr. Jose Chavez in civil engineering, where this study was funded by USAID, the Agency for International Development, supporting the student exchange and also the research collaboration between CSU, University of Utah, and the US-Pakistan for Advanced Studies in Water, US Center for Advanced Studies in Water. So AJ, I'd like to turn it over to you and give more details on the technical report.
Well, thanks, Alan. I'll start sharing my screen so everyone can see. All right, Thomas, can you see this okay? Can you hear me, by the way?
Yeah, you are loud and clear.
Great, thank you. All right. Well, thank you, Dr. Indales and Dr. Chavez and Dr. Gates for being here. I appreciate it. And you as well, Dr. Borch, being remotely. I see you. So I'm going to go ahead and let's see. And everybody's seeing my shared screen and not me talking right now. Is that correct?
No, we're seeing you.
Oh, we're seeing me. Okay, let me fix that really quickly first. Okay, how about now, Dr. Borch?
That is perfect.
Great. All right. Well, as Dr. Indales mentioned, my thesis or my technical report for my master's is done on, it's titled Improving the Assessment of Salinity Hazard in an Irrigated Field Affected by Environmental Gypsum. And so jumping right in, I'd like to start with the pop quiz. I always like to get everybody a little bit comfortable before I jump into a heavy topic because, master's thesis are always about that. So these three items here, we have drywall, toothpaste, and then maybe the oddball of the bunch, global food insecurity. What do they all have in common? And if I was lecturing right now, because as I've taught for Alan's class, I'd wait awkwardly until everybody answered. But in this case, I'm just going to give you the answer. So the answer in this case is salt, specifically gypsum. Gypsum is the primary ingredient in drywall for putting walls up in your house. It's also a large ingredient in toothpaste that gives it that nice creamy texture. And global food insecurity is clearly influenced by salt, and I'll show you, but that's what we're going to focus on next. Global food insecurity is majorly influenced by salt, because this map right here points out to us where in the world salt is a problem. And let me just start a little before that. So this is the Harmonized World Soil Database, and that basically means it's a map of soil characteristics by the United Nations all over the world. And I've made this map in a way that highlights salt content that is in levels where anything that has a color on this map that's not gray is an area that's hampered by salt. So that means that crops cannot be grown to their full potential or can't grow at all. And that is a major problem, because you can see that $27 billion here on that bullet point annually is lost just because salinity is a factor in our soils and our agronomic lands. And annually, we're losing it. It gets worse. It compounds. 3.7 million acres of land are lost each year due to soil salinification and sodification. And another thing that I want you to keep in your pocket for later is that out of all this land, 21%, or about 1/5, is considered gypsiferous, which is a type of salt, but we'll get into that later. So how did all this salt get there? Why is this an issue, and why do they exist? So there's a couple sources of salts in our soil. And the first one is the basics, geology. So salts are minerals, and they come from the weathering of minerals. So probably our number one threat to food insecurity is erosion, which ultimately ends up in what we're talking about here. So when minerals erode and dissolve, they become more basic components, and a lot of those components are salts. The next source of salt is climate, and that is a good rule of thumb for anybody who's not familiar with salts, is that, remember in chemistry, we have salt to water, and then we boil the water, and then all the water's gone. What's left is the salt. This is essentially what's happening in our soils too. Any place in the world where there's more evaporation and water use by plants than there are irrigation and precipitation, you're inevitably going to be accumulating salts, and that's what that represents. Another source is water reuse. So this is becoming a more popular topic as water scarcity becomes an issue. The river is diverted, it picks up salts in a field, it goes back to the river, and then we reuse it again. Or maybe in an urban setting, we take gray water from a water waste treatment plant and we use that to irrigate. All of these types of water contain salts, and so we accumulate salts the more we reuse a single source of water. Human activity, plant fertilizers, manure, compost, de-icing, wastewater, a lot of things that humans do end up in salt accumulation. Water tables. If you have a water table, and that means water in your soil is coming up to the surface from like an aquifer or something like that, those water tables will bring up with them salts in many occasions from either a separate source or directly from the soil that's underneath what we are growing crops on. And then we have seawater. This one's probably the easiest. It's like, oh, of course, seawater's salty, but it becomes a problem, and it's becoming a problem for coastal areas, especially where their source of fresh water is an underground aquifer, and the seawater intrudes into it, and it can connect hydraulically with that aquifer, that essentially poisoning the well, if you will. And then finally, coastal breezes. This is such a small contributor, but it's fun to mention because it's very strange. But as coastal breezes, pick up aerosols from the ocean, they will deposit salts as well on the land as the breeze hits there. So it's easier to explain visually. So I made this little graphic that kind of helps. And this is an agricultural situation. So this is an image here on the very left. We have a model that I cleverly designed of a pivot irrigation system. And so we have our wheels and our sprinkler there, and that illustrates that water is being applied onto our field and there's salt in that water. And then we have our plants and they're using water. And then also water just evaporates off the surface. Combined, we have what's called evapotranspiration. And so similar to my metaphor of boiling water in a pot and leaving salts, essentially now you can see what's happening in our field. The plants use the water leaves, but the salts stay there. And in this case, I also put a separate source of salt from a high water table, where if it's high enough and it's on the border of that, what we call the vadose zone, or where the root zone meets the deeper zones in the soil, that interface can be highly salty because the salts are drying up and leaving there constantly. So that's kind of a visual way to look at it. And I mentioned that there's a couple different types of salts, because salt isn't just what's on your table for dinner. That's one type, and that's here at the top, NaCl, sodium chloride. But as you can see in this table here, we don't need to go into depth about all of them, but just understand that there's many types of salts, and we need to differentiate them. And why? That's what this slide is about. So differentiating salts is important because primarily we're interested in soil structure and what that does to everything else. So saline soils, and that means that the primary salt is sodium chloride, or sodium. Sodium could be mixed with something else too, but sodium is the key word there. So saline is the opposite of sodium. I have that backwards. Sodic is sodium, saline is everything else. So figure A, saline, let's say calcium sulfate in this case, which is gypsum. We have a soil particle here in figure A that illustrates what calcium does to clay. So soils have a negative charge. And when calcium has a positive charge, specifically with two bonding sites, any soil particle that has a negative charge is going to want to latch onto it. And the calcium has an extra hand essentially to hold on to. So calcium salts, calcareous soils, and things of the like with two or more charge sites will bind soils together to have aggregation. And the opposite occurs when you have a sodic soil, which remember is sodium based, or single charge site here, which is figure B. So in the same kind of situation, when sodium is your primary site, you can see here that we have sodium ions, which only have one charge site. And as a result, when it hits one particle of clay, the charge balance in the chemistry is very happy. So it does not need to aggregate to make sure that both hands are held. And so when that happens and you have a soil with lots of sodium in it, it will do what's called dispersion, and it'll turn into like a powdery dust. And when that happens, a lot of things start to become an issue. The soil breaks down, the water infiltration gets harder. It's harder to just do many, many things because you're essentially just trying to grow in like dust. So we need to understand how both salts work, because it's understanding how they work and how they affect the soil is how we treat it, how we account for it, how we manage it. And so I want to give you guys an example, because what we really need to understand is how do these salts hurt plants in the first place? And there's a couple ways, but the biggest way that we studied is what we call matrix potential, and that's essentially suction. So I have an image here that shows you what I call the suction pathway of how plants uptake water. So plants suck on water just like we suck on water through a straw, and they maintain a gradient of suction all the way from the soil out into the sky. So up here at the top, you'll see that we measure air, and we can measure that in like something that you fill your tire with, pounds per square inch, or PSI. And it's negative because it's a suction. So air, we're putting here at negative 8,000 PSI. The leaves of the plants have negative 200 PSI. The roots have negative 50 PSI. And now you can kind of see that as long as that gradient is maintained, the water will move through the plant and out into the air, as long as that chain isn't broken and that gradient is maintained. So in our first hypothetical situation on our plan on the left, I've added some salt, and it's a very low salt. It's got minus 5 PSI. So is that gradient maintained? Will the plant uptake that water? Once again, I'm going to give you the answer. The answer is yes. So we have a negative 5 is greater than negative 50. So therefore, the water is able to move through the plant and out into the air as normal. In the middle plant, we have a similar situation, but I've added a little more salt. So now we have negative 25 PSI. Once again, that's still okay. We're able to successfully move the water through the transportation gradient there. But now over here on the very right, I have a very salty soil, and it's got negative 75 PSI. And guess what? We have an issue here. Because once again, the roots are only at negative 50. So if the soil salt is sucking harder than the roots are, that water gradient is now broken, and it is no longer able to successfully uptake that water, and the plant will start looking thirsty and dying. And that's essentially one of the major ways that salts will hurt a plant. But there's a few other ways I'd like to mention just for the sake of completeness. A second way that salts can actually hurt plants is ion toxicity, or in layman's terms, it's essentially poisoning the plant. Certain salts in too much quantities, if you eat it too much, just like if you eat too much table salt, it's poisonous. Same thing with plants. If they eat too much salt, they will die because it causes other metabolic issues within the plant itself. And then the third and final way that salts will hinder plants, kind of an indirect method, but still worth mentioning, is that salts, because of their nature of wanting to grab onto things, will actually physically get in the way of other molecules trying to be uptaken into the plant. One most notably is nitrate. Nitrate goes up into plants through water and passive osmosis. But if salt is in the way and dissolving into the water, and then the nitrate can't get into the water because there's too much salt there, all of a sudden the plant starts experiencing nitrogen deficiency as a result, even though there's probably plenty of nitrogen, or maybe plenty of nitrogen in that soil. So those are the two other ways that are contributing factors to salt damage in plants. And so now that you understand how salts are, how they're damaging, we need to understand, how do we measure it? How do we understand if we're going to be damaged? So I want to talk about a few methods. There's actually a lot of ways. This is a very studied discipline. Salts have been around for aeons. But one of the most common ways that we measure it can be split into two main categories, either electrical conductivity or total dissolved solids. Now, electrical conductivity is based on the principle that salts are electrolytes, just like in your Gatorade. Electrolyte means that if dissolved in a solution, it will make the solution more conductive when exposed to electricity. Total dissolved solids is simply the number of particulates per million in a volume. And so I want to specifically highlight a method that's kind of what we call the gold standard in salinity research, because it's what everything else it tends to be based off of, and that's the saturated paste extract method. As you can see in this image here, I've made some of them in my lab, and what we're trying to do is we take a soil sample, we dry it, we grind it up, we then add pure water that's deionized to it, and then we mimic a saturated soil. Essentially, it's a qualitative process in which we add enough water that it becomes a paste, but not so much that it becomes a liquid. It maintains certain properties. But this is the standard because we're trying to mimic the saturated root zone, completely filled with water. And once we have that reading, it's the saturated paste extract reading. Let me just reemphasize here, you may have read it on the slide. The electrical conductivity of the saturated paste is called ECE, or electrical conductivity of the extract is what it stands for. And ECE is the measurement, like I said, we've been using in salinity literature for a very long time. And this graph shows you how we use it. So on the x-axis here, where it says DS per meter or MMOHO per centimeter, that is the measurement that we use, or the units that we use to measure EC. And so it's a conductivity level. And as you go from 0 to 30, you can see we have some lines drawn here that mimic or essentially tell us or inform us how much yield that you should expect to lose if you were to grow a certain type of plant in that setting where there's salt in the soil. And so we have very sensitive plants down here on the very left bottom of that graph, where if you put very little amount of salt, you're going to start losing yield, all the way out to very tolerant things. And so if you have a soil with salt in it and you can estimate this loss, that helps you make management decisions as to, should I change crops? Should I try to fix the soil? What should I do? And it's all about, it becomes an economic decision at that point. So here's a table. We don't need to go through all of them, but I wanted to give the audience an example or some examples of what fall into sensitive, moderately sensitive, all the way to tolerant. And so something very sensitive like strawberries, they start losing yield very early. In fact, it's the general literature accepted value is after 1 decisiemens per meter, that's very little amount of salt, they'll start losing yield. Whereas something like barley is very tolerant and it won't lose yield until around 8 decisiemens per meter. And the other way to understand, so like I said, if you understand the crop salt or the crop tolerance, you can make a decision as to whether I should change crops if that's more economical, or maybe I should try to fix the soil. So part 2 of this discussion is if I were to take the second route of fixing the soil, what would I do? There's some equations here up, but understand in principle, the way that you would remediate a soil is to add extra water that's good quality that you can then dissolve the salts in the soil and push them down and outward out of the root zone. So a couple assumptions: you need to have good drainage for this to work, but assuming that you have good drainage, you can apply extra water to push the salts out of the root zone so that the plants are no longer inhibited by the salt in the soil. And these equations illustrate how you would calculate that. So if I know the salt in the soil, and I also know the salt concentration in my irrigation water, I can create what's called the leaching ratio, or how much, it's a ratio between the salts in the soil and the salts in the water. And then you take that, and there's a relationship between that and how much water is needed by the crop in that day. Let's say we have the crop of, something like a corn let's just say it needs 1 inch today. And we have an example of, in the water, we have 1 decisiemen per meter salinity. And in the soil, we have 2 decisiemens. So if you plug it into this equation, I can say, I can say that if you apply 1.13 inches of water today, you should be able to alleviate the issues of salinity accumulation in your soil by over irrigating. So this is important because, let me go back. This is important because understanding that we need to accurately measure what the impacts on our crop yield are and accurately measure how much water we need to apply is crucial to understanding our salt issue and how we might remediate it and what the economic impacts are. But here's a problem. So if our standard is the saturated paste, the saturated paste method is actually not the perfect method, right? It's the best that scientists came up with at the time to try to figure out what's going on. And gypsum is not friendly with the saturated paste method. So over here, I have a problem where gypsum can actually dissolve more in your lab, believe it or not, than out in the field. So I say that sarcastically. So on our left, we have an image here where we have a gypsum crystal that's in an aggregate. And I've put some water pathways here, and you can see that it's actually pretty hard for water to get into an aggregate and dissolve this gypsum crystal out in the field because it's so nice and protected. But if I take that sample out, I dry it, I grind it, I expose it to all sorts of different elements and different concentrations of CO2 and things like that, now all of a sudden the water is readily able to touch that gypsum crystal and dissolve it. So now we're having a situation where what's happening in the lab isn't a representation of what's happening in the field, and therefore can really mess up what our management decisions could be. Because if I go to my table and I say, oh, it's 2 decisiemens per meter, I should switch crops. Well, if it's a gypsiferous soil, maybe it's only 1 decisiemen per meter actually, but because you did it in your lab, you're getting an inflated value. All of a sudden, you may make the wrong decision, or you may over irrigate if you're trying to remedy your situation through leaching fractions and over application. So there's a large potential for waste if you don't have an accurate salinity value. And so once again, just to re-emphasize here, overestimate the true salinity hazard in an area will result in over-irrigation and overestimation of yield losses. And so what can we do about this? Well, now we're finally here to the point, this is what we need to talk about. This is what our team in the room decided to try to investigate. And we also wanted to figure out a methodology for maybe applying these corrections over a larger spatial extent, because doing a single sample is valuable, but doing a whole field is much more valuable when it comes to practical and pragmatic management decisions. And so how did we do this? I want to introduce, like Alan said earlier, my study site was the Arkansas River Basin of Colorado. And so here's kind of a visual representation of where that exists. So if you're familiar with Colorado, down in the southeast, we have the Arkansas River. And to zoom in on that, we have a satellite image of the river itself, and we have what's separated into called the upstream study region and the downstream study region. And we primarily focused in the upstream study region of the Arkansas Valley, and particularly on a location near the town of Swink, if you're familiar. It's where I went to high school. Shout out to the Lions, in the Fairmont Drainage District. And so what's the Fairmont Drainage District? The Fairmont Drainage District was actually a result of the 1918 Colorado Drainage District Act, which basically said that we acknowledge that there's a lot of drainage and salinity issues in the state because of irrigation, where we have a river, we divert that river with canals, we apply the water onto fields, and then it creates water table issues because so much water is being spread out and added to the aquifer in places where it may never have been before humans were there. And so the Drainage District Act gave funding for farmers and others and districts to install drainage tiles, in this case made out of ceramic, that are installed underneath root zones to allow water to be put into these tiles and then moved away from the field to get them away from the crops and stop hindrances of salt accumulation. And so unfortunately, this one is being over 100 years old now. It has a lot of imperfections. And so we chose to study this place because, well, guess what? It has drainage problems, and that goes hand in hand with salinity issues. So we found a few fields in there, and I'll talk about how we found them. So in the Fairmont Drainage District, we decided that we were going to take a bunch of soil samples and do some educated surveying of salinity. Well, how do you do that? In the bottom right of this slide, I have a picture of me dragging what's called a electromagnetic induction device. So that's kind of a fancy term for a device that shoots electricity into the soil to measure how much salt, water, and clay is there. And so we drug this device over many fields, about 200 hectares, which were surveyed here with GPS equipment and a handheld data logger. And it makes a map of, like I said, once again, moisture, salinity, and clay content, or soil texture, if you will. So we need to be able to separate out just the salt part because it's biased by all this stuff right now. And so once you have this reading that's influenced by all three, you go out and you take a couple soil samples, and that's a picture up in the top left there of my crew helping me do that. And you take those soil samples to go back to your lab, run the saturated paste, and then you can now calibrate your readings that were taken with your EMI instrument to the lab manually measured samples of saturated paste, and that becomes a map. So let me show you how many samples we took. So this is a map of the field and where we sampled in one of our surveys in 2018. So over these 17 fields, we drug our instrument. We then generated this map after statistical calibration of our soil samples to our EMI readings. And then from this, we were able to identify two fields that we wanted to more heavily survey for our study because they were irrigated and under irrigated corn specifically. So corn is relatively sensitive, so we wanted to see what was going on there. And these are the two fields that we identified. As you can see, there's some hot spots in this lower left field, and in the top spot, it's got a nice gradient as well. Low spots are dark green, high spots are red. And so once we're able to do that, and we found these two fields, I'm zooming in on them now, what we were able to do, or what we intended to do, was really heavily monitor what was going on with the salts in the soil. And so to do that, and to see what effect that the gypsum was playing there, because these fields were primarily gypsiferous, and they had some sodium in them as well. But we were able to install what are called soil suction lysimeters. And these are devices that are essentially straws that go into your soil, and they suck out what's called pore water. So without disturbing the soil, we irrigate the field, and then the water goes into the soil, and then we suck it out with these devices, and we can get a relatively undisturbed reading of what's actually happening in the soil as far as the water goes. So at those locations where we installed these pore water suction lysimeters, We also took soil samples every time that we extracted that water. So this allowed us to see, in a situation where we look at the pore water and we also have a soil sample that's analyzed via the saturated paste extract method, we can now compare them to a disturbed sample and an undisturbed sample. This has not been, a data set like this has not been performed to this extent before or in this type of setting. So this was pretty unique. And we ended up, because of how hard it is to get these samples, it has to be fairly wet to obtain pore water extracts. We were able to get about 54 paired samples. So once again, that's 54 pairs of pore water coupled with a soil sample that was analyzed for saturated paste and also moisture content. We also took moisture content at the time of pore water extraction. So, and with that, here's some extra things, because we need to more fully understand these soils to be able to understand some of our correction methods. So as a survey overview, we collected some physical parameters, including bulk density, field and saturated paste water content, cation exchange capacity, temperature, and then some chemical parameters. So this includes all of our major ions and cations here, and calcite and gypsum, of course. If we're going to study gypsum and how it affects things, we need to at least annually take samples for how much gypsum and calcite are in the soil. Partial pressure CO2, how much CO2 is in your soil. We modeled that with what I'll explain further down, and then some predefined values of cation selectivity coefficients. We can go into that later with my committee, but for everybody else, just know I collected a lot of data. And so now let's get into the actual correction process. How did we attempt to do this? Method 1 is actually a method that was proposed and published in the SSAJ journal, or the Soil Science Societies of America journal, in 2016 by a group that was using a model called Extract Chem. Extract Chem is an equilibrium geochemical model. And essentially understand that means it uses equilibrium chemistry to predict changes in ion concentrations, or the salt concentrations in a soil, based on changes in moisture content in that soil. And so this is, now you're starting to see why I may have to collect so many values about my soil, because to run a model like this, you really need to understand and have a lot of characterization about your soil to run it. And so this method, largely, the way it works is, think about it in theory. I have a model that can predict ECE. And so what I'm going to do first is I'm going to take a saturated paste and I'm going to model what that is. And I'm going to try to predict what it's doing. And the model usually does a great job at that. And so I can predict the EC in this model. And then I'm going to say, dry this sample down hypothetically to a field level of moisture, or field capacity, for example, and then see what happens. And so that's the first step. You take saturated paste, you dry it down in the model, and you observe the ion changes that are used as outputs. And so then you take those outputs and you start to step 2. So step 2 is to take a soil that's down in the field and take those ions and then simulate it back up to the moisture content that you started with in your saturated paste. But the whole thing that makes it a gypsum correction process is that in both of these steps, you explicitly say in the model that gypsum concentration is 0, as opposed to what it actually is, what you observe in the soil itself, in situ. And so in theory, by doing this, you're creating an EC value that is no longer biased by gypsum, because it's as if it was never there. And that has a lot of assumptions, but that's the first method. So it's a very intense modeling way, uses a lot of parameters. Here's another method that's actually, in our research, we went back to a very old method and readapted it to fit our situation. So if the first method was published in 2016, the only other literature that we were able to find for our study was published in 1962 about this topic. And essentially what it says is, here in the purple box, the scientist Leon Bernstein said that in a gypsum soil, I can predict what EC should be based on what we understand gypsum conductivity to be in a saturated solution, which just means dissolve as much gypsum in the water as you can, and then measure that conductivity, which happens to be 2.2 decisiemens per meter. And then he also said that without gypsum, this is the equation that you would use to predict a soluble salt solution. So in this case, we have two ways. If you have a gypsum soil, this is what you would use to predict your salinity. And in a non-gypsiferous soil, this is what you would use to predict your salinity. And understand that essentially what's happening here is that theoretically, in a gypsum soil, what he's proposing is that if you normally take a soil that is completely soluble, you dissolve it by what's called a dilution factor, or the ratio of your current state of water to a different state of water. It just becomes a dilution. But in a gypsum setting, the assumption here is that the gypsum soils never fully dilute. In fact, we're going to subtract out the gypsum concentration of 2.2, dilute it normally, and then we're going to add the 2.2 back into it. And this is going to give us a representation of what the gypsum is actually doing in our saturated paste in theory. So our team moved those, kind of massaged the equations around a little bit. We massaged it because the idea is that if you can have a prediction with gypsum and a prediction without gypsum, if you subtract the difference between those two, you can now get a theoretical shift or difference between the two. And if you do that, you subtract the blue portion from the purple portion, you now have what I'm calling delta EC, which is now a function of the moisture contents alone. And so finally, if you want to correct and develop what I'm calling ECEG, ECEG is a ECE value that has been corrected for gypsum bias. And in this case, if we have an ECE value that was affected by gypsum, and we calculate delta EC, if you subtract that, you are now able to obtain a ECEG value, or a value that is corrected for gypsum bias. Similar, that now ECEG is also the same output of the first method, just to be clear. So with these two methods, we wanted to apply them to the data and the 54 pairs that we obtained in the Fairmont district. And before we could decide, which samples needed corrected out of those 54 pairs, we had to come up with a way to figure out which samples were biased and which are not, because we need to justify that before applying the correction. And so this is what we did. We have two charts here. On our left, we have and we used, let me start again. We started by simulating, remember, the saturated paste within extract chem. And extract chem did a good job at this, except for in cases where we include the gypsum. So here on the left, we have a graph where on the x-axis, we have ECE, and on the y-axis, we have the relative difference between measured and modeled values. So what we observed in the lab versus what the model produced. And you can see here on the left, we have this weird tail that's occurring here on the left side of the graph. The values became very biased and then all of a sudden tapered off close to zero. Now, in the model, on the right, we have the same graph, but this time I left the model without gypsum in it. And when you do that, all of a sudden, there's hardly any tail. There may be some evidence by this point up above at around the 250 mark, but there's no evidence of that. So what is that doing? When I run the model and I don't change anything except for the fact that there's gypsum in there, and let me just also pretend that we left the initial and final model moistures the same concentration in this case. So really, the only thing that we're testing in the model at this point is equilibrium. Is the solution in equilibrium? And so on the left, because when you include gypsum, you're getting differences from what the model predicts, that's telling us, the scientists, that those solutions are not in equilibrium with respect to gypsum. Now, all of these samples set overnight as per the methodology of the saturated paste extract to try to reach equilibrium, but these samples never made it. So as such, we were able to determine that 17 samples were not affected by gypsum because they never reached equilibrium in gypsum. The rest, however, are potential candidates for gypsum bias. And we found this threshold to be 3.1 decisiemens per meter. So if it was above 3.1 in our case, it was affected, and if it was less than, it was deemed not affected. Now, just to further robust my justification for this, these samples were collected over 3 years in 2 fields, and so we did not find explicit differences between years or irrigation changes, things like that happened in the fields between those years. These sample sets were consistent throughout all 3 years of the study. And so once now we're going to get to the real meat. What happened after we applied our correction methods to these samples that we deemed gypsiferous and biased by gypsum? So over here on the left side, I want to just compare the methods one more time as a reminder. The selective dilution, or the Bernstein method that I talked about there earlier, or created by Leon Bernstein rather, it requires 3 inputs. That is the EC of the soil, the water content of the soil in the field, and the water content of your saturated paste. It also doesn't require any labor outside of the data already collected for correct electromagnetic induction surveys, which is important. But unfortunately, the accuracy of this method has been untested. It's very unstudied. So accuracy, take it, no pun intended, with a grain of salt. And then finally, uncertainty is large. The EGM method, however, in contrast, requires 19 soil parameters to run the model and run the method. So it requires significant time, labor, and expertise to be able to operate the model successfully. But it is more accurate in theory. I mean, we are using more advanced and more chemistry backing and real soil science to determine this value. That's the nature of coming out in 2016 as opposed to 1962. But however, the uncertainty is large in both, and we'll talk about that at the end. So just remember these 2 methods for now. After the correction, I just want to mention this too. So we applied our correction to both, or to the affected samples in both methods. And this is a 1-to-1 plot. So what that means is on the x-axis, we have ECEG, which is, remember, corrected for gypsum bias, on the x-axis, and on the y-axis, we have ECEG derived from the selective dilution method. So the dotted line represents a perfect agreement. If all the points were on that line, the methods would be identical. And in this case, they actually agree very well. So that means regardless of how differently they produce their values, and they actually agree fairly well in this setting. So that's optimistic for us as we move forward, because we're trying to find an easy way to correct for gypsum. So the methods, even though vastly different, agreed in this case. And so we wanted to then further go ahead and try to see if there was relationship with the original ECE values that we obtained from the field, and then use that as a way to predict ECEG over a larger extent, over the whole field instead of individual samples. And so these 2 plots represent both methods. On the left, we have selective dilution. On the right, we have EGM. And on the x this time is the observed ECE value from our lab. And then on the y-axis, we have our ECEG value that we corrected and derived with our 2 methods. As you can see that there's very strong linear correlation with both methodologies to the original ECE values, which, recall, are very biased by gypsum concentration in the soil. So if that's true, and we're able to successfully create these what we're calling a meta model to create a relationship between ECE and ECEG, we might be able to use this model to apply it to other samples that were not used in this correction data set, and that's what we're proposing here. So let me take you how we might do that. So this is a method summary of how we might go about correcting a field or 2 or a region for gypsum bias in our solutions or in our ECE readings. So the first step is to perform a survey of ECE. Remember the EMI survey, identifying the fields? That's what the first step is. That's what we've done. Secondly, we need to identify 2 locations or more where the soil properties are representative of the larger area. In this case, we chose 2 fields out of our 17, and we chose those 2 fields to study more heavily to use and develop develop and calibrate our models for the gypsum correction. And so once we were able to do that, we were able to apply the gypsum correction using the pore water samples that I took. Remember, these are for validation and uncertainty quantification. And so once you have this correction factor and you've developed a corrected ECEG value for every ECE value, you are then able to develop our meta model and then take that meta model and apply it to places where we have ECE that are we're unsampled essentially. So we're extrapolating or maybe interpolating, for example. In this case, we're interpolating, but extrapolation is kind of the next step. So we're able to use the meta model to correct ECE values that were not part of the gypsum correction process. And then finally, you may want to take those ECEG values and then actually apply them to the yield loss model that I mentioned earlier. That would give you a more accurate, in theory, representation of the salinity in the soil so that you can more accurately measure yield loss and irrigation decision-making for remediation. So in this case, I'm going to point out what that might look like. The red line, dotted line, represents the threshold slope model, what we call them, for corn. So corn is relatively sensitive. Here at about 1.2 decisiemens, it starts, or 1.7 decisiemens, it starts losing yield at a 12% rate. So it's moderately sensitive. And so what does that mean? Here, let me show you some maps where we actually followed through with this whole process on the two fields. And on the left, we have maps A, B, and C. And these are maps of salinity. In the top left, A represents the raw reading of ECE that we took and did with our mapping process. B and C represent corrections that have been applied through the gypsum correction process and then corrected with the meta model to adjust the salinity that we observe for gypsum bias over the entire field. So in B, it's selective dilution, and C, we have the EGM model. So you can see from both B and C compared to A, there was quite a significant drop in salinities visually in these two maps. Shifting your attention over to the right, we have the same kind of map, but this time we've ran the EC values through our yield loss model. And so now we're mapping yield loss. And so green represents no yield loss, red represents lots of yield loss. And so up here on A, once again, we have this really hot spot in our field and we're losing lots of yield there. But in B and C, where we correct for that with our gypsum correction methodology, you can see that our yield loss may not actually be as much. And so this, in theory, might be a more representative way to figure out what the impact on your field is. And here's some graphs that kind of illustrate what that looks like. If we were to go ahead and use this the meta model method, we went ahead and analyzed what that looks like as far as where can you save, how much will you save, what is the percentage that you're actually gaining from doing this, XYZ, these type of things. So in our left, we have a box and whisker plot that represents first ECE, ECEG, and ECEG from selective dilution. So the middle is EGM, the right is selective dilution. So these graphs are kind of a detailed way to explain to you, essentially in words, that first off, if you look at the whole field as part of, remember that the whole field wasn't biased by gypsum. Our threshold was 3.1 decisiemens per meter. So if a raster value or a pixel in that field was not greater than 3.1 decisiemens per meter, it was not affected. But if you look at it as a whole field, this correction doesn't seem to make as much of an impact. So the blue box and whiskers represent all raster cells. So if you looked at the whole field. The orange, however, represent just looking at the cells that we deemed biased by gypsum. And when you compare them this way, what you'll find is that the ECE values are very high and the correction becomes very significant. So on the very left here, for example, where we have ECE, the average tends to be about 4 decisiemens per meter. And the average downshift, however, is 1.5 decisiemens per meter with EGM and 1.2 decisiemens per meter for selective dilution. So remember, this is all important in the context of the crop we're trying to model. So if we're trying to predict the yield loss of corn, which starts losing yield at 1.7 decisiemens, if we have something that we measure as 2 or 3 decisiemens, but it's really actually 1.5 less than that, you're right there in the area where you may not actually need to start making management decisions yet. And it becomes significant because you don't want to have that inaccurate representation. So, or let's say, for example, an easier situation, strawberries. if they start losing at 1 and you measure 1, but it's actually 0 because of this gypsum correction factor, you don't actually need to take action yet. So it's good for thresholds of making decisions. Now on the right where it says YR%, this is a similar kind of effect that you might see in the yield loss setting. So once again, if we have ECE, which is the bar on the right where it says YRECE, you might actually expect a lot of yield loss in those situations that are greater than 3.1 decisiemens. You know, the average yield loss is somewhere around the 75% mark. But when you adjust it for gypsum, you actually get about a 6 to 13% increase in your average yield for those gypsum bias. So this really helps with those economic decision making, the economic decisions that you need to make to whether to say I'm switching crops or I'm taking action, because you may not need to take action yet if you have a gypsum bias situation. And another point that I'd like to make out is that in these fields, based on the threshold slope model, there was actually occasions where the salt was so high that we would have expected the crop to die entirely. It should have been 0% yield seen, but that was not consistent with what we observed in the field. We didn't see anything die because of salinity or water. And so making this correction was congruent with our need for a bias correction because none of the corn was dead, even though the model said it should. But here's a big problem with both of these methods and why there's a lot of need for future work, as with any science. This is a chart that is coming back to, remember when I said I took pore water samples? Well, this was as a way to measure the correction accuracy and uncertainty of both of our correction methods using this study. Both correction methods can predict the pore water concentrations of salinity, or excuse me, rather the EC in the pore water. And we have the real answer of what that should be. And there has been no work to date about verifying the correction methods using real pore water yet, and to see if these methods are actually accurate in this transformation process, because there's a lot of chemical activity happening here. And so what we observed is this. Once again, this is a 1-to-1 plot. If the methods worked well, or let's say if the methods were good at predicting the pore water EC, they would all fall on the 1-to-1 line. But as you can see here, the points are all over the board with a trend that says that as salinity increases in what we observe in the field, the uncertainty around our model predictions gets larger. So unfortunately, that means like as we get more salt in our soil, our method for correction becomes more uncertain, and there's a lot more room for improvement in there. So we need to make sure that in the future that we kind of investigate and understand why this might be. And so I guess we've kind of reached the end. So once again, ECE is a common measure of salinity, and it's used as an index for crop yield reduction. But in gypsiferous soils, excess gypsum, it biases our saturated paste analysis, making it harder for us to make accurate and good management decisions. So in our study, ECE was corrected with selective dilution and equilibrium geochemical modeling. And then on top of that, we used the relationship between the corrected ECEG value with the original ECE value to come up with a meta model to estimate gypsum corrected ECEG over the entire study field. And then what we observed also is that significant changes in yield loss predictions occur when accounting for gypsum. We were hoping and observed that yield losses would be less, and that was congruent with visual findings that we saw in the field. And so, like I said, this study leaves a lot of room for future work. Probably the biggest area for improvement is our benchmark of comparison. We presented two methods today to correct for gypsum, but as we saw with the pore water data, neither one of them performed well, or at least it would indicate that they don't perform well at this EC transformation between water contents. And so we want to perform an experiment where we're able to control for that and do a dilution experiment where we saturate paste and leave it and see at different equilibrium times, maybe 1 day, 2 days, a week, who knows, extract EC and figure out where the bias starts occurring and get a better idea of what the true EC-EG value is. Secondly, we need to collect corn yield data because, like I said, we visually saw that corn didn't die, but we need to run that through with real corn data, and that's future work to come. We did do that, but it's not presented here. We need to verify that our EC-EG values are congruent with what the model should expect. So essentially the question is, if we take our yield data, it should fit better when we correct it as opposed to when we don't. And so that's what we need to test next. And then thirdly, correction methods should be explored with EC 1:1 and EC 1:5. So I didn't mention this much, but saturated paste is a very hard procedure relatively as far as labor and time. And a more common method for measuring salts in soil is equal parts soil water, or maybe 1 to 5 parts soil water. And that's used much more prolifically around the globe, but it is not well understood how much gypsum bias these solutions. And so we'd like to investigate that. And then finally, sources of uncertainty are very great and need to be explored with more data in a more controlled setting. So once again, our site was in the Arkansas Valley, where it was an actual observational study managed by a real farmer. That leaves lots of sources for bias, data issues, uncertainty, you name it, there's a lot of issues. So maybe in this case, a controlled setting where maybe gypsum salts are the only yield loss factor could produce a more accurate depiction of what's actually happening in the soil and how we might go about correcting for it. However, after that, you'd want to go back and retest it out in a field setting and make sure that it actually works. So this is kind of the chicken and egg of science and how it needs to work. So we discovered we need to do a controlled testing, then we'll go back and hopefully validate it. And with that, I'd like to just briefly mention before we go into questions, fun pictures and other projects of my own as I've been on this journey. First off, I'd like to thank my committee for allowing me to go to Pakistan, not one time, but 2 times to work with colleagues that we had over there. It was great to be able to work with them and understand and learn. We worked with the university in Jamshoro, the Inuit is what it was called. Anyway, I've made many great relationships, and Dr. Gates even has a student from the university over here as a PhD student right now. It was a wonderful experience. IoT projects. Throughout the way, one of my biggest interests was technology in agriculture, technology in irrigation and salinity management. And so from Dr. Jay Ham and his crew, I'd like to give a shout out to them for teaching me so much for how to do various things such as create soil moisture sensors all the way to taking an old data logger system and making it cloud capable and smart, if you will, so that I didn't have to drive the Rocky Ford just to figure out if somebody irrigated or not. It was great. And then 3D printing, of course, and stuff too. That's all very fun. Finally, here's just some fun pictures. This is me and my crew. I like to catch snakes. Luke Engler on the left likes to catch birds. Brian likes to dig holes with his ponytail. And that's me out in the field after trying to extract some soil pore water. You can only do it, like I said, when it's very wet. So I was wearing shorts and muck boots to go out there and collect water samples. Once again, collect snakes, water samples, and sometimes the soil is very hard, so you need a very strong crew to help you dig those holes. And then down on the left we have my friend Rustin, who is helping me analyze yield data. And then, as Ellen mentioned earlier, I'm currently managing the Irrigation Innovation Consortium Farm as Assistant Director. It's been a wonderful exposure to the irrigation industry and all of my colleagues and a bunch of industry people, and it's been a wonderful experience. I've learned so much, and it's really bolstered my ability to be a scientist. So I thank the IIC for that. And finally, my next steps here, I'm going to be transferring to a new department with CSU in the Agricultural Water Quality Program on December 1st. So I'm really excited for that new opportunity as a scientist. I'm going to be continuing my PhD in salinity technology and our data analytics, building off this data with the future work I described. And I'd like to work on the soil signal sensing company with Dr. Jay Ham, Ian Asklin, and Dylan Casey. But most importantly to me, at least in the immediate future, is I'm getting married. So next April, me and my fiance Emma are getting married, and I'm so excited. So thank you for everybody for joining today. And I'd like to shout out these extra special people in my life. And I'll turn it over back to Alan. Thank you.
Good job.
Thank you, AJ. We're opening it up to questions now. If you can.
Okay.
Any questions from the audience online? And feel free to also use the chat. And I guess the committee is holding back for the
Yeah.
the formal Q&A from
The committee gets to grill me afterwards, so please ask some questions now before, to warm me
I
up.
have a question. I have a question. Thanks for that great presentation, AJ. I wanted to just ask, based on your experience, if somebody wanted to put in like, are there like easy IoT sensors to do electrical conductivity that you can set up in a field? And if so, what kind of density would you like say, maybe how many sensors would you recommend per acre to do active monitoring of salinity? Or would this be something that you would think would be good for management?
Thank you, Garvey. That's a great question. And so just to bust it down for the audience again, there's two parts to this question. The first one is there a sensor that can help you monitor salinity in the field? And it's IoT capable, for example. And then the second part of the question is, how many would you need and where would you put them to make management decisions out of it? So the first part of the question is, yes, there are sensors out there that can detect salinity in the form of EC. It gets infinitely more complicated than that afterward, because EC, once again, is water, salt, and soil texture, but it gives you a really good idea. Now, as far as how many and how to put them in the field, I think that really comes down to understanding the characterization of the particular area that you're working with. Let's say if it's a single field, you may need to understand where the hot spots and lows and not so hot spots are, because it comes down to a statistics question of management zones. In our case, we use the EMI technique that allowed us to try to characterize a large region first, which then helped us narrow down where we think sensors might go. So an easy way to answer your question is to say, figure out where the decisions are most important and try to place some sensors there using an informed methodology. Use a low-cost way to a high-cost way. Always start there, the cheapest way. Maybe you don't need to perform an EMI survey, Garvey. Maybe you just ask the farmer, where are your salt hotspots? And you start from there and you look, and then you look at other areas that may not have high spots and maybe low spots, and you try to make management zones out of that. And then I would say, make sure that you have your sensors in those management zones. So as far as statistical robustness, and if you're trying to publish it, the answer is never enough. You never have enough sensors in the field to do what you really, really want to do, but we always try to get close. Does that answer your question, Garvey?
Yes, it does. Thank you.
Oh, great. Thank you.
Dylan has a good question on the chat.
Yeah, okay, so Dylan asked me, would port water samples be biased by EC/major ion chemistry of the irrigation water versus saturated paste samples that are extracted with DI water? Would it make sense to use irrigation water for saturated paste samples to more closely replicate what the plants might, quote unquote, see? I think you've really touched on a major issue with the observational nature of this study, Dylan, because the answer is that if you wanted to see what was actually happening in our field, I would tend to agree and say that you'd want to use real irrigation water, make your paste, and see what's really happening, because that's the better direct comparison. But because we're trying to establish a methodology of how this gypsum correction might work, we want to stick with the standard, because the purpose of the study was not to try to change the saturated paste extract method to say you always need to use local water and make it and then see what happens. The intent was take a methodology that was already used and try to develop and use and understand a correction method for that so that it can be applied anywhere. But I think that is a good area of future exploration, Dylan, that if we were to do that, you might get a different story and maybe the uncertainty would be less in our setting and perhaps the modeling perhaps would go much better, I would hope. So does that answer your question? I think so.
Yeah.
Okay, any other questions?
Yep. Well, having no other questions, I'm sure AJ is welcoming further questions, but via email or personal phone call maybe.
That's right. I think everybody on this call has my phone number, so just
Yeah.
give me a call.
Yeah. So thank you once again, AJ, and thank you for the audience online for participating.
Yep. And thank you for my Arkansas Valley folks to attend today. I appreciate it.